Hi, guys. How you guys doing this morning? I know, I'm tired too. It's also really dark. It's really dark here. How many of you guys have traveled already and are dialing in remotely? I had some students in my 8 o'clock class who were actually somewhere else other than Boston. They traveled already, and actually that's a benefit of the remote classes, right? That you guys can not miss a class because you can dial in from wherever you are. Great. All right, so we're going to let other people join us. Let's see. Oops. Speaking of which, let me do this. Okay. So today I just finish up chapter 2.2, which is just this final part of our last example on our lecture examples page, and then we're going to start chapter 2.3. Okay, in my 8 o'clock class, we got, almost to the end except for the last example, and then we'll finish that up again on Monday next week. Just as a reminder, obviously there's no quiz this week. Okay, holiday, but we will have a quiz next week. That will be our last quiz of the semester, which is next Thursday, and I think that will include all of chapter 2 that we've studied so far. We should be able to cover pretty much all of chapter 2. Anyway, we can play it by ear. We'll talk on Monday when we come back, see how far we get. Anyway, let me know if you can't access any of the homework assignments. They should all be up there, okay, and enabled for you to take a look at. I believe most of them are due next Thursday. There shouldn't be anything due this week, as I recall. If there's something due this week, don't sweat it, because I take late assignments anyway. Okay, so let's go ahead and get started. So this is looking at lecture examples. This is where we left off with last time. So this is lecture examples for chapter 2.2. Okay, and we were on the last example, which was we wanted to find the area under the graph of f of x equals x, which basically just forms a triangle. Okay, so we're looking for this area here, of this triangle. We did it with geometry. Okay, 1/2 base times height. It's a right triangle, so we can do that easily. And then we did it using our right approximations. Okay, and we don't know how many subintervals we have, right? So we're going to take the limit of our right. Okay, and then we're going to finish up. And we're going to do our left subintervals. Okay, so this is our last example as we're working our way through for this particular chapter. Okay, sorry, my papers are all over here. Okay, so L sub n. So L sub n, right? Let's come up with the formula for L sub n, and then we're going to take the limit for that. Okay, so L sub n, remember, delta x sum j equals 0 n minus 1. This comes from the stuff that we talked about last time. Okay, delta x is the width of our rectangle. F of a plus j delta x is the height of our rectangle. Okay, so now remember, we calculated our delta x last time as 4 over n. That was equal to our delta. So I'm going to plug that into here. So this is going to be 4 all over n sum j equals 0 n minus 1. F of, we're starting at a equals 0. So 0 plus j times 4 over n, right? So this is going to equal to 4 over n sum j equals 0 n minus 1. F of j 4 over n. Okay, our function f of x is equal to x. So this is what I'm going to plug in. So because f of x equals x, I plug in this wherever I see x. What am I really going to get? I'm going to get 4 over n. Give me a sec. 4 over n, right, times the sum j equals 0 n minus 1 of simply j times 4 over n, right? I plug that into my function, which happens to be just equal to x. Okay. 4 over n is a constant term, right? I'm going to factor that out. So what I'm going to get is 4 over n from before times 4 over n from here, factoring it out, times our sum, right? So I'm just summing up. 0 plus 1 plus 2 plus 3 plus all the way up to n minus 1. Okay, remember we had a formula. We did those power sum formulas for summing up j values. So that's going to give us 16 over n squared. That comes from here. Times, when I just sum up j like that, I get n minus 1 times n all over 2. Okay, when I, cancel, it's 2, divide by the n's, and then I distribute, I've got an n minus 1 here, right? When I distribute that, I'm going to get 8 minus 8 over n. Okay, so this is my L sub n formula here. Okay, so I need to take the limit of my L sub n, limit as n goes to infinity of L sub n. Okay, so I'm going to plug in what I just figured out of my formula for that. So I'm going to go as n goes to infinity of 8 minus 8 over n. Okay, n's going to infinity. 8 over a really ginormous number gets super small. This thing goes to 0. So our limit basically converges to 8. Okay, which is what we would expect. That's what we got on the right. And that's actually what we got for our geometry. Okay, so it's a pretty good confirmation that we're probably on the right track. Okay, so it was your last lecture example for chapter 2.2. And I will scan this in later and post it up onto our Canvas page in addition to the lecture video for today. Okay, guys, I'll give you a second to write that down before we move on. Okay. All right. All righty. So very exciting. We're moving on to chapter 2.3 today. 2.3 is called the definite integral. Remember when we first started talking about integrals, there was indefinite integral, right, which didn't have bounds on the integral signs. When I do the indefinite integral, I integrate and I have to do plus c because I don't have a specific value. When I do the definite integral, I'm going very specifically across the interval a to b, right? So I integrate my function with respect to x over the interval a to b, okay? So what this means is we're taking a look at our function just from these values here. It's a very specific idea, okay? So this is essentially an area under our curve, okay, from A to B. But let's write down, we're gonna talk a lot about background information, like where does this come from? Because we're gonna be using the definite integral and the integral, of course, too, a lot, right? It forms the basis for what we're doing. So like we did with the derivative, we have to talk about what does all this mean in the background? Like where is all this coming from? It's not just some magic happens, right? So we're going to talk about where does this come from and what does it mean, okay? So let's just take a step back and remember what we did in chapter 2.2. So chapter 2.2, remember, we did L, our limit, was equal to the limit as n goes to infinity of our right? This is where we did the rectangle. Let's just I'd have a rectangle and my height was here. This is my delta x. I'm going to sum up all of those rectangles. My delta x is constant, right? And I'm hitting it right on the right hand corner of my rectangle. This is equal to the limit as n goes to infinity of my left. Remember this one. Here's my delta x. Here's my left, which was equal to the limit as n goes to infinity of my middle, which was, this is my rectangle, delta x, my middle, was a middle point right there. Because we're going to sum up all those areas. So L, all of these limits equal to each other, they're all approaching the same value. Okay, so we'll say our function f of x is continuous on an interval a to b when our function is greater than 0. We're going to talk about both when the function's greater, when the function's positive and when the function's negative. But for now, when the function's greater than 0, L is equal to the area under the graph. Specifically, it's the area between the function and the x-axis. Okay, so it's kind of like, you know, here's my x-axis, here's my y. here's my function. And I'm going to go from A to B, right? So, right, my function is positive, so it's got positive values. It's above the x-axis. This definite integral represents this area here between my function and the x-axis, and also bounded by A to B. Okay, so this is like what we're talking about here, this area. So call that L. That's our area. Make that green so you can see that better. Okay, that's our L. All right, so let's talk about Riemann sums. There's a lot of definitions in this chapter. I think I said that already. So let's remember our R sub n, L sub n, and M sub n. These are kind of a form of Riemann sums. They're not specifically Riemann sums. We're going to talk about how they're slightly different, but R sub n, L sub n, M sub n form an idea. They're just like a Riemann sum, but these are made of rectangles of constant width, delta x, right? Which, remember, we factor that out. We say delta x times the sum of all the heights, right? But that's like basically saying base times height plus base times height. But the base has the same width. So it's a constant width. And height, f of x, where x is a point on the rectangle and the function. So it's where the rectangle hits the function, essentially, right? So like we did here, it's the right, it's the left, it's the middle. Okay, this is where our function passes through. Okay, so it hits that spot. The delta x's are constant. Okay, now in a Riemann sum specifically, it's a lot like this, an awful lot like this, except that the rectangles need not have equal width. Okay, they don't have to have the same delta x. Okay, and the height of the rectangle can be measured at any value within that delta x value. The height may be any value of f of x on that subinterval. Okay, so R sub n, L sub n, N sub n, I've got constant delta x, right? And then I've either got on the right corner, left corner, or middle point of that rectangle. Riemann sums are an awful lot like that, except that the delta x's can vary. Okay, and then my function value can be any point along that rectangle. Okay, that can be, I'm going to do that. We're going to see why it doesn't matter as we go along. Just like we did with here, we're going to increase our n to infinity so that our delta x's become so tiny, it isn't going to matter that we're basically varying the width. Okay, all right, let's talk about some definitions. We've got some vocab, basically we all need to have to be on the same page. So a partition P of size n is a choice of points that divides our interval a to b into n subintervals. Right, so I can say P is equal to my partition A, my first one, x naught, which is less than x1, which is less than x2, which is less than or equal to, so on and so forth, which is less than or equal to x sub n, which is equal to b, right? So my first one is A, my last one is b, right? And they're all like gradually increasing along that interval, okay? That's our partition. Our sample points, we're going to use these values here to define our delta x's, right? So each subsequent value, I'll draw that in a little bit, because we're actually going to do it out, right? These things form a delta x, these things form a delta x, and so on and so forth. These things form a delta x. Oops, draw that backwards, delta x. Okay, so this is delta x0, delta x1, delta xn. Okay. Okay, so our sample points Don't worry if you can't read my delta x writing, we're going to actually do it out so you'll see it. Our sample points, C. C is going to be defined C1, C2, so on and so forth, C sub n. Okay, these are values that I'm taking within that delta x. These are x values. I'm going to take these values and I'm going to plug them into my function. I'm going to get like a height. Okay, so each C sub I belongs to the sum subinterval. So C sub 1 has to be within this x0 to x1 range. Okay, I can't say C sub 1 is going to be anywhere. It's got to be within here to here because I'm going to then find a height that corresponds to that particular rectangle. So it belongs to a subinterval x sub I minus 1 comma x sub I. So the one just before it to the one that we're looking at. Okay, so for all I, I'm going to use that to define my delta x. It'll make sense when we work through an example too. Okay, you guys all have this before I turn the page? Okay. Another vocab. It's called the norm or a mesh of P, and it's written like this. It's like a double absolute value sign. This is the maximum of the lengths of our delta x sub I. So this is the widest delta x that we have, right? So we've got all these like various delta x's, right? And we want to find out this value here, the norm or the mesh of P, is the widest one that we have. Okay, so let's go ahead and let's draw it out just so we can conceptualize. So here's x, here's y, here's my function. Okay, so I'm going to start at A and make this as my delta x, and I'll do one here, and I'm gonna really exaggerate it. So here's another delta x. I'll choose a point here. Here's another delta x. I'll choose a point there. Here's a delta x. I'll choose a point there. You get the idea, right? See, I'm making them. Here's a delta x, and I'll choose a point. I'll choose a point. Let's see here, right? So, and I'll call it a day right there. So you can see I'm really tried to exaggerate it. My delta x's have different widths. My function, I'm just basically choosing, values within this rectangle to pick out values of my function. Okay, so let's write it down. So I've got a rectangle, has a height. It's our function evaluated at whatever that C sub I is going to be along our x range, right? So within that delta x, right? So it's the function evaluated that gives us the height. And it's got a particular rectangle has base delta x sub I. So delta x sub I, sub I, sub I, sub I, sub I, these are all different delta x's, right? So this delta x and this C sub I need to evaluate to get the base and the height, okay? Over each subinterval x sub I minus 1, x sub I, okay? And then we'll say each rectangle has area f C sub I delta x sub I, okay? And that's true if our function is greater than or equal to 0. If our function evaluated that is greater than or equal to 0, and it has a negative area if the function evaluated at that C sub I is less than 0. So I want to, if my function yields a negative number, I'm going to multiply it by a negative to give me positive. Okay. So let's come up with a definition of our Riemann sum. Okay, definition of a Riemann sum says, I'm going to call it R is a function of f, that's the function we're doing, p, the partitions, and c, the sample points, is going to equal to the summation I equals 1 to n of the height times the base, right? We're summing up the areas of all the rectangles again, which is equal to f of c1 delta x1. Sorry, you can't see that. Plus f of c2 delta x2 plus so on and so forth, plus f of c sub n delta x sub n. I'm just going to sum them all up, just like we did before, right? This is also sometimes written in our book like this. R, P, S, and F. This here, the S sample points, sorry, is what we've been calling C. So S is our sample point. So some books call it S. This is a P, right, for our partition, and then F is a function. Okay, you can write it like this, you can write it like that. Just depends. Some books write it one way or the other. All right, so I've got my lecture examples for chapter 2.3. And I've got the function 8 plus 12 sine of x minus 4x on this interval. So I've got my function, I typed it into my calculator, I graphed it out. It looks like this, right? Except I'm going from 0 to 4. So I'm only going from here to here on that interval, right? So let me draw it out on here just so we can see. I always like a visual. And let me see if I can get this right. Okay, so let me graph this out. It looks like. Yeah, so this is what we're dealing with here. Okay, so we're going to be able to find the area from 0 to 4. So we're given, I didn't write this down, but we're given different values. So I'm given my partition, x0 starts at 0, which is less than x1, which is equal to 1, which is less than x2, which is 1.8, which is less than x3, which is 2.9, which is less than x4, which is equal to 4. So see, we go on our interval 0 to 4. Okay, so that gives us our partition values. Okay, which means I can use this to help me draw out my rectangles. So I'm going to go up to here. There's one, to here's another one, 2.9, here's another one. And then here is another one. Okay, so let me draw these. And yeah, I know what these values are already because I wrote it out, but this one goes down to here. There. Okay, so these are the rectangles that we're working with. And we're given our sample points, C. They're going to be equal to 0.4, 1.2, 2, and 3.5. I had to give you those, right? So that you can use it to draw out your rectangles, and we're going to use it to calculate our delta x's. And we also want to know what is the norm for the mesh equal to. Okay, we're going to calculate that as well. Okay, so let's think about our solution. So my first step is I need to calculate my delta x's, right? So my delta x1 is going to be x1 minus x0. x1 minus x0, so x1, that's equal to 1. Delta x2, that's going to be x2 minus x1. So x2, 1.8 minus x1 is 1, 0.8. Delta x3, this is going to be x3 minus x2. So that's 2.9 minus 1.8. It's equal to 1.1. Delta x4, which is equal to x4 minus x3. See, notice I'm using the the current one minus the previous one to tell me what my delta is. So this is 4 minus 2.9, that's equal to also 1.1. So I need to look on here. Remember the MASH, this, you know, norm of P is like the biggest delta that we have. So these two are equal to each other. So this, right, that's our largest delta X value. I guess I just answered that question there. It's equal to 1.1. Okay, but now I've got all my delta X's. Okay, I'm going to use my calculator to get the values f of c sub I. And you can do it in a couple different ways. You can plug it into your function. I did it on the graph. I did second calc, and I said value, you know, 0.4, and tells me what my y is equal to, and I can copy that down. There's going to be some rounding, so my answer is going to be approximate, right? So I'm going to say r f p c is equal to, remember, we're going to sum up our height times our base. So f of 0.4 times delta x1 plus f of, I'm getting this 0.4 from the values here that were given to me. So f of 1.2 times delta x2 plus f of 2 times delta x3 plus f of 3.5 times delta x4. Okay, I plugged in these values here into my function. Make sure you're in radian mode, otherwise this is going to come out garbage. Okay, so this is approximate because I had to round. This was 11.07 times 1, that's my delta x, plus 10.91 times 1.1, plus, oops, sorry, 1.1 plus, I forgot the other one, 14.38 times 0.8, that was this one right here, I forgot that, plus minus 10.2 times 1.1. Okay, I'm going to add these up. This is going to be equal to 23.35. Okay. It gives us our Riemann sum. We're adding up the areas. And it's like approximate because I had to round. All right. All right, so let's keep talking about our definitions here. So let's talk about our function and let's draw a picture. So here's my graph, x, y. Here's my function. Now imagine that my delta x's, right? My delta x's are getting smaller and smaller and smaller. We did this before with the other stuff too, but let's draw it out here as well. So my delta x, remember they're variable, but they're getting smaller and smaller and smaller, right? Between our a and our b value. Okay, so let's talk. So the rectangles corresponding to a Riemann sum with our mesh, our norm, that's a small number, right? Which means that I've crammed a lot of rectangles in a finite space. A large number of rectangles in a finite space, right? I'm going to go from A to B, okay? So we can write this in math. So I'm going to say as n gets bigger, right? My delta x, my p gets smaller. Remember this one represents the biggest delta x that we have. So my biggest delta x gets smaller, goes to 0, okay? Okay, so if that's true, then we can say therefore our function is integratable, it's integrable over the interval a to b if all the Riemann sums approach the same limit, L. Okay. So as our largest delta x gets super small. Okay, so let's write it down into a definition. So I'll say L is our limit as our biggest delta x gets really small. So as our norm of P gets small of our Riemann sums, which is equal to the limit. Okay, as P goes to 0 of, let's do it out. So this is I equals 1 to N, right? We're doing the area of the rectangles, C sub I, delta X sub I. We're going to sum up all those areas, right? That's what the whole Riemann sum thing is, okay? So now, this is our limit. This is the value that we're getting, okay? This is our Riemann sum, this is our limit. So let's do this. If the absolute value of our Riemann sum minus our limit, right? This is like a magnitude. So I'm taking the difference between our limit and what I'm getting for the Riemann sum. If that gets small as our norm of P gets small, right? So what this means is our limit and our Riemann sum. So the difference between them, as that difference between those two different values gets really small, that means that there is no difference between them, right? As the number of subintervals, as the number of rectangles gets really big, as their delta x gets really, really small. This is going to lead to the definite integral. So let's do another definition. Okay, so the definite integral of our function f of x over our interval a to b is the limit of our Riemann sums, right? So just like our definition of the derivative had some theory behind it, right? It was like the slope, the limit of our, secant lines, right? Is that, difference between our secant line and our tangent line got really small. That gave us the definition of our derivative. Our definition of our definite integral also is similar too, right? It's based on this summing up of all these rectangles. Okay, so watch, I can go the definite integral a to b, f of x dx is equal to the limit, right, as my delta x gets really small, of our Riemann sums right? All I'm doing is adding up the area and saying I'm going to add up the area, right? So delta x, dx is another way of saying delta x, right? The function evaluated at a value, the function evaluated at a value, and I'm going to go from a to b, right? These values, c sub I and delta x, are based on our a to b range, okay, our a to b interval. So this integral is really, it's a summation, right? Delta x dx is this infinitely thin slice, right? That infinitely thin slice, it's got like a thickness of, like an infinitely thin thickness right here, and it has a corresponding height. I'm going to add up all those little infinitely thin slices, and that's going to give me the area under the curve between a and b. Okay, that's what we're trying to do here. So when the limit exists, we say f of x is integrable over the interval a to b. Okay. Let you guys finish writing that, and then we'll turn the page. Actually, I'll scroll up just a little bit. Now I can write it like this. I can say a to b, f of x, d of x, or I can go from a to b, this is an a, sorry, of f of t, d of t, or I can go from a to b, f of u, du. It doesn't matter what my function as a function of what variable is, right? I'm doing this delta of that variable, right? And this is the function, this is the height, this is the base, right? All different variables. It's the same process. So let's write down some details. Okay, so the process that we're doing is integration. F of x that we're integrating over is what's called an integrand, right? That's the thing that we're integrating. A and B, these endpoints here, are the limits of integration. Okay, R, F, P, C is an approximation, right? So I go to take the integral, right? But it really, the integral comes from summing up and doing the Riemann sum and making my my width of my rectangle really tiny and the height, you know, very specific. But my Riemann sum itself is an approximation, right? And so like, why do we care? Why are we doing it? Well, this is good for proofs, right? I can use it in proofs. It's good for functions that are discontinuous. Perhaps I can. Running out of space, discontinuous functions, right? It's also good for functions that aren't easily integratable. I should be able to take the integral of e to the x squared from a to b, right? But I mean, all of the tools that I have so far, I can't take the integral of that. I don't have derivatives inside. I can't do, you know, use substitution or integration by parts or anything like that. I can't do power rule. So a Riemann sum is going to give me a really good approximation of what that integral is, especially if I do a lot of subintervals along here. A lot of our calculators, right, are going to do Riemann sums actually when they calculate things. They just do a lot of subintervals, okay? And processing speed is getting cheaper and cheaper, so we can do that more easily, okay? And then we can think about a to b, f of x dx, which is the limit as the rectangles get thinner, right? They become this little like slice, okay? So let's talk about a theorem. So we'll say if our function is continuous, there's a lot of theorems and definitions in this chapter, continuous on our interval a to b, or if the function is continuous with at most a finite number of discontinuities. So we can work around them. Then we say that our function is integrable on our interval a to b. Okay. Let's do an area. We're going to talk about assigned area. So let's talk about definite integral as a signed area. What do I mean by that? All right, let's take a look. You know, I like my drawings. X-axis, y-axis. Here's my function. Just something like that. And say I'm going to go from A to B. Right? I've got a couple different intervals here, right? So I've got an interval here. And I have an interval here that I'm taking a look at, right? Well, this area between the function, so this is our function right here. This area between the function and the x-axis is a positive area. This area between the function and the x-axis is a negative area. My function values are negative. Okay, so I need to be able to think about what's happening when I'm being asked a question, right? If I'm just going to integrate blindly from A to B, it's going to be assigned area where I essentially subtract, right, my negative area from my positive area. We're going to write all this down, okay? Okay, and if I want to make sure that I just have the magnitude of that, I have to take this value and then make it positive. We're gonna talk all about it as we go. So let's start writing it down. So when our function is greater than or equal to 0, so that's this portion of it. When our function is greater than or equal to 0, the definite integral defines the area under the graph in the x-axis, right? So it's between the function and the x-axis. If the function takes on both positive and negative values, we define the idea of what's called assigned area. Okay, and how we're going to define that is we're going to say our assigned area of a region is equal to the area above x-axis minus area below x-axis. Okay, we're going to subtract these when we just integrate willy-nilly from A to B. Okay, so that's like saying A to B, f of x dx is equal to the assigned area between graph and x-axis over the interval A to B. Okay, so it's not taking into account the fact at all that the function goes below the x-axis and I'm dealing with a negative value. I'm going to end up subtracting these. Okay, if I don't want that, if I want them to be positive, I need to figure out where that range of values is that becomes negative and multiply it by -1 to make it positive. We're going to do an example like that just so you can see. Right. So my example in number 2, we've got the function. We're going to integrate from 0 to 5, the function 3 minus x dx. So let's go ahead. I'm going to graph it out so we can see. We're going to go from 0 to 5. 1, 2, 3, 4, 5. And then this is 1, 2, 3. Minus 2. So I'm going to graph it here, here, and here. So the function looks like that. Okay, so what I'm looking for is this and this. Okay, I'm going to be finding the area, these areas here. Okay, so we take that integral. This is what we're doing here. All right, so now let's go ahead and do it. So I'm going to do integral from 0 to 5, 3 minus x. I'm going to do my, we haven't learned it yet, the linearity. So 0 to 5 of 3 dx minus 0 to 5 of x dx, right? So this becomes 3x minus 1/2 x squared, evaluated from 0 to 5. If you have no idea what I just did right here, don't worry about it. We're going to talk about it on Monday when we meet again after the break. Okay, that's called the fundamental theorem of calculus. We're going to actually go through it. Okay, so now I get to evaluate. So this becomes 3 times 5 minus 1/2 times 5 squared minus 3 times 0 minus 1/2 times 0 squared. Okay, and then this becomes essentially, this is equal to 2.5. Right, this thing is 0 right there. Okay, can you guys all see that? Okay, so now just as a contrast, we weren't asked to do it, but I just want to show you how it's different. If I say, let's compare it, let's calculate 0 to 5, the absolute value of 3 minus x dx, right? So I take this same function here, and what I'm going to do differently is the areas that were negative now become positive. Right, so that's our absolute value. Okay, this is absolute value of 3 minus x. Okay, so let's go ahead. What does that mean? That means I need to identify the region that's positive, and I'm going to integrate across that region so I can see it from the graph. We're going to learn next semester how we actually figure that out algebraically. Like I'm going to set this equal to 0 and solve for x, and then I need to test the value, see what's positive or negative within that interval. Okay, but let's do this. So I'm going to go from 0 to 3 minus x dx. That part's positive. Now, if I want to make a negative number positive, I have to multiply it by a -1. So I'm going to integrate from 3 to 5 of the same function, right? This is taking the absolute value of it, right? I have to figure out the areas that are negative and then multiply them by a -1 to make them positive. Okay, so this is what we're doing. We're breaking up our integral into positive and negative segments, okay? So let's go ahead and evaluate. So this is going to look like 3x minus 1/2 x squared evaluated from 0 to 3 plus 3x minus 1, sorry, that's a negative minus x squared from 3 to 5. Okay, sorry, this is a minus. Okay, so we're going to do the same thing like we did before. So this goes 3 times 3 minus 1/2, 3 squared, minus 3 times 0 minus 1/2. I don't usually plug in the zeros, but I'm just showing you here. Minus, now watch, so I'm going to do 5. So 3 times 5 minus 1/2, 5 squared, minus 3 times 3 minus 1/2, 3 squared. Okay, add it all up, this part goes to 0. Okay, so basically what we're dealing with here, right, I'm going to do it all, there's algebra that's happening here, but then in the end I get this is equal to 6.5. So the total area, the magnitude, is equal to 6.5. The signed area, which is this part minus that part, is equal to 2.5. So be careful and make sure you're reading the question, because if you just plow through 0 to 5, you're going to do a signed area. Okay, if you're calculating the magnitude, that means you need to identify the regions that are negative, right, where the function goes below the x-axis, and multiply them by -1, and then you can, right, by subtracting, and then you can just add all those areas together. Okay, so far so good, guys? Okay. All right, so let's talk about some more definitions. There are a lot of definitions. So some more definitions. We'll talk about properties of a definite integral. So properties of a definite integral go like this. It's theorems. A theorem, we've got the integral of a constant. We'll call it C, constant C. So it's like I'm going to go from A to B of C dx. So remember when we said before we're taking the integral of C dx, right? I would just get C times x plus some constant term. But now I'm going to go C, it's going to be B minus A. We're going to actually talk in great detail about this in the next chapter section. Okay, so roll with it. This is kind of like us introducing an idea before we've explained where it comes from, but this will help you if you wanted to start the homework for this chapter section. Okay. Theorem, there's a linearity, which we just did in the previous example, linearity of definite integral. We did the linearity of the indefinite integral in the previous chapter, but the linearity basically applies when I have two functions being added or subtracted together. So I'll say individually f and g are integrable over our interval a to b. Okay, so I'm going to go a to b f of x plus or minus g of x dx. Now I get to distribute my dx and my integral sign to each of these things here. This only works for addition and subtraction. If you try to do this for multiplication or division, it will come out completely wrong. Okay, so we have other tools for handling multiplication and division. Linearity is just addition and subtraction. Okay. Plus or minus. All right. And also what I can do is, if C is a constant, I can say A to B, C, f of x dx. We did this before. I can bring my constant term outside of my integral, process my integral, right? And then multiply by C at the end. Right, let's take both of these and we'll apply them to example 3, even though we kind of did it already in example 2. We'll apply them to example 3. So we're going to go from 0 to 3, 2x squared minus 5 dx. Okay, so my linearity, this is the subtraction, so I can use linearity. So that's like saying I'm going to go from 0 to 3, 2x squared dx minus integral from 0 to 3, 5 dx. Well, I have a constant term and a constant term. I'm going to bring those out. So 2 from 0 to 3 of x squared dx minus, bring the 5 out, 0 to 3 dx. Okay. Now I'm going to get 2. I'm going to do my power rule. Let's write that down. So this is, we're going to do power rule here when we go to integrate. So this is going to be 2, like we had before, times x cubed all over 3. Remember, I increment my exponent by 1 and I divide by the new exponent, minus 5x, and I'm evaluating both from 0 to 3. Okay, so now we go ahead and do that. So it's going to be 2, 3 cubed all over 3, minus 5 times 3, minus, I'll plug in the zeros, even though that whole thing's going to go to 0, 2, 0 cubed over 3, minus 5 times 0. Okay, so this whole thing goes to 0, right? And this is 18 minus 15, so this area is equal to 3. So with a definite integral, we're getting a specific number, okay? It's giving us the area, signed area or otherwise, depending on what technique we're using. All right, another property that I can do is I can reverse the limits of integration, but I have to do it in a specific way. Right, so in general, if A is less than B, right? So let's say I'm going to go integrate from A to B, f of x dx. Maybe I want to go from B to A, f of x dx, right? Well, B is bigger than A. Well, this is equal to minus, right? If I'm going to reverse the limits, I have to multiply by negative, okay? Go from A to B becomes minus B to A, okay? So example 4 says, let's show that the integral from the integral from 5 to 0, x squared dx equals minus 0 to 5 x squared. I guess let's go ahead and do that. So what I'm going to go is like this. I'm going to say, so if I integrate from 5 to 0, x squared dx, that's going to equal to, remember when you're going to do the power rule, so it's going to be x cubed over 3, evaluated from 5 to 0. And that's equal to 0 cubed over 3 minus 5 cubed over 3. Okay, let's do the other one. I'm going to go from 0 to 5, x squared dx. That's going to equal to x cubed over 3 evaluated from 0 to 5. That's equal to 5 cubed over 3 minus 0 cubed over 3. Okay, so I've got minus 5 cubed over 3 and 5 cubed over 3. So that's going to be equal to a minus times that. Check. Okay. You guys good so far? Okay. We have a couple more properties to do. So our definition, when A equals B, our interval becomes a to a. So a to b equals actually a to a. It's a point integral, right? So if I go to integrate from a to a of f of x dx, I'm going to get it equal to 0, right? You can imagine I'm going to evaluate my function at a, subtract it from my function being evaluated at a. That's why I get 0. This also tells us that when we integrate, we are integrating over a range of values. I'm not integrating at a point. I can't get the integral of a point. Okay, the area of a point is just 0, right? So when I integrate, I have to integrate over a range of values. Now that range of values can be super small, right? I can go from 0 to 0.000001. Well, that's not 0 to 0, it's 0 to 0.0. It's infinitesimally small. So my integral is still a range of values. I can't do a point. I can do what they call additivity for adjacent intervals. Okay, it goes like this. So I start at A, and I want to end at C, and B is some point between A and C, right, in my interval. So, and I'm going to say that my function f of x is integrable along this interval. So I can go the integral from A to C of my function, right? I'm going to go part of the way, A to B plus integral from B to C of the same function dx. We did this before when we were figuring out the absolute value of that function, right? We broke it up. We still integrated across the whole interval, but we broke it up part of the way. Okay, but I'm adding up. Okay, so this is important. We actually end up using this part a lot. Okay, so now let's think about another definition. Our last example we'll do on Monday, but I want to leave you with this definition here. It's a theorem. It's called a comparison. So f and g are integrable. And we say g of x is less than or equal to f of x. We'll draw a picture in a minute. Okay, for x values in our interval a to b. That means when I go to integrate from a to b of g of x, that area is going to be less than f of x d of x. Let's think about that graphically, right? Remember, this represents an area. So here's our x-axis, and let's say, all right, g of x. Here's my g of x function, and I'm going to go from a to b. Remember, when we integrate g of x, I'm talking about an area here. So that's g of x, right? Now, f of x is greater than g of x, right? So when I go to integrate from a to b of f of x, I'm looking at not just this region, but this region too, right? So the area of f of x is all this orange part, and the area of g of x is all this orange, is all the green part. So if g of x is smaller for these values in our interval, smaller than f of x, right? The area that I integrate for g of x is going to be less than the area I integrate for f of x. That's what this is saying right here. I'll give you a last definition, last theorem, and then we'll do our example on Monday. So let's say I have a lower bound m. We'll draw pictures just so we can imagine it, but I've got some m values, a lower bound, and that's less than my function. My function is less than uppercase m, which is an upper bound. Okay, this is for all x in our interval a to b. Okay, and for f of x in our interval a to b. Okay, so now what happens is this. I'm going to integrate all of these. I'm going to integrate from a to b, my lower bound. I'm going to integrate from a to b, my function. I'm going to integrate from A to B, my upper bound. Okay, what's going to happen is this. When I go to integrate this, I'm going to get m times b minus a. It's going to be an area, right? This is the base times the height. Now let's say my function is too complex for me to integrate, so I just have to leave it as an integral, right? Often you will find, and we're going to learn more about this next semester too, you'll find there are functions that are too complex to integrate using the tools that we have so far. So I need to specify a lower bound and an upper bound for my area. Okay, so I can't come up with a specific value for the area under the curve of my function between a and b, but I can come up with a range of values. It's going to be between 5 and 10, say, for example. Okay, so let's say that the integral lies between the areas of the two rectangles, b minus a and capital M, b minus a. And this is important because, you know, we're learning these tools for how we can get the definite integral or the integral in general, but sometimes the functions, I just can't plug them in and do them. I don't, the tools that I have are approximations. Okay, so let's draw a picture just so you can see what it looks like and why we would do this. Here's our x-axis, here's our y. All right, so let me think how I want to do this. So my function, so here's my function. Okay, and I'm going to go from A to B. Now let's say my upper bound. Yeah. So my upper bound, I'm going to try to make it as close to my function as possible, but my upper bound is going to go like this. Right, so the area of my upper bound is going to be this rectangle right here. Right? My lower bound, right, say I'm going to try to make that lower, so I'm going to make that small. So my m comes down to here. So my area for my m, my lowercase m, is this bit right here. Now I cannot calculate the area under the curve of my function, right? But I know it's somewhere like right around here. It's this thing. Okay, so what we would say then is I've got this green rectangle. This is my big M, right? This is my upper bound on the area. And then my lower bound on the area, do that in, what I do that in orange. My lower bound on the area right? And my function value, my area of my function is like, it's like this. It's somewhere in between these two, okay? And I don't know, for some reason, I can't integrate it. I have to be able to approximate it and say it's between 5 and 10, right? I don't know what this is, or it's between 8.9 and 9.2, say, for example, because I can't integrate it for some reason, whatever it is. But I want to be able to approximate it. So this is how we would do it. There's an example for this. It's example 5, and I'm going to do it at the beginning of class on Monday when we meet again. Okay, guys? Hey, have a safe holiday. Stay safe, stay healthy. Okay, and I'll see you guys all in a week. Okay, enjoy your break.
Thank you.
Thank you.
Thank you.
Bye.
Thank
Take
you.
care.